right, so this week we are talking about 6-4, 6-5, and 6-6. So for 6-4, we're going to be starting on page 323. So the first thing we're going to be talking about is graphing square root functions. So at this point, we've learned quite a bit about radicals and how they can be rewritten as exponents when they're fractional. And we've talked already quite a bit about graphing square root functions. So we are kind of already attuned to a lot of this. So the radical function for the square root function, it looks like this. Oh, and again, this is on page 323 in your own book. This square root x doesn't have the radicand, the index, but we always assume the index to be 2 when it is the square root. So if it doesn't have one, you assume it's a square root, so it's a 2. And this is what the graph of this looks like. It starts at 0, 0, goes up, and it starts decreasing. So there's quite a few things in real life that follow this pattern. Pressure in a tube. So like when you first turn on the water, it increases rapidly, and then it kind of just stays the same because there's only so much you can put into the tube. Let's see, losses and decreases in money, as well as losses and decreases in anything physical like electricity or energy. Those all follow these square root curves. So that is something that you will see kind of in real life, and I'm hoping to bring in somebody to talk a little bit more about how they use it in their career. Okay, so this is the parent function, and the domain for this parent function is that x is going to be greater than or equal to 0. I think my light got turned on. Oh, there we go. And then that y is going to be greater than or equal to 0. And you can see it starts here at 0, 0, and then keeps going. And the ending behavior is as x goes to 0, y goes to 0, and as x goes to infinity, y goes to infinity. So again, we've already talked about parent functions and how we can transform these functions. So this part at the bottom of the page on 323 is just talking about how you can transform a square root function just like any other function. So this a value changes the slope. So any multiplication is going to stretch or compress it. And if the a value is greater than 1, that it's going to vertically stretch. And again, it's outside of the x grouping, so it's stretching in the vertical direction, or the y's. So anything grouped inside with the x's, like this h, is going to be shifting left and right. And x's always lie, so with this being a negative here, that would shift it right, actually. And then the k value just switches it up and down. And y's don't lie, so it's just what it looks like. So if it's a plus k, then it's up, and if it's a minus k, then it's down. The other thing that can happen is our a value can both be a fraction and a regular, or a number larger than 1 or smaller than 1. We already said that. But it can also be a negative, and a negative would flip it over the axis, just like this little line up here. So a negative would flip it over the x-axis because it's affecting the y's. Okay, let's do some problems from your book on our note paper. So make sure you have your own note paper out so that you can do this. Okay, and in my my vocabulary portion in green, I am just going to write that the square root function of x looks like this, so that I know what my parent looks like. This is the parent function. That'll make it easier to remember. Okay. So, example 1 says to identify the domain and range. And example 1 in your book is on page 324. Okay, and it says identify domain and range of 2x minus 6 plus 1. And remember, we always write it on this side in black. example 1, page 324. And we put identify domain and range for or of f of x equals square root of 2x minus 6 plus 1. Okay, so our domain starts with our parent function. Don't forget to rewrite it over here. I always start to explain before. Radical 2x minus 6 plus 1. Okay, so back in Module 3, we learned about how square roots or radicals cannot have negatives under them. We learned about this when we did the quadratic function that creates imaginary numbers. So the domain, or where we can plug in an x, is going to be very much affected by what is grouped with the x's. So we know that whatever is inside has to be greater than or equal to 0. It cannot be negative, is essentially what we're saying. And that's because it would make an imaginary number. So the first thing we're going to do is solve for x by adding 6 over. So then we should have 2x is greater than or equal to 6. Then we divide by 2. And we go over here. X is greater than or equal to 3. So this would be our new domain. Our domain is going to be shifted up 3, or shifted to the right 3, or left 3, sorry, my bad. And then this right here is switching the y's, and so our y is actually just being shifted up 1. So y is going to have to be greater than or equal to 1. So these are our domain and range. So we just did example 1, so let's move on to example 2. So remember, we're going to write it in black. So example 2 says to graph the transform square root function. So we are just going to say graph. Oh, I'm also going to put example 2 above it. Page 324. So graph g of x equals -3 square root of x plus 1 plus 2. Okay, so we're going to write the same thing over here. Graph g of x equals -3 radical x plus 1 plus 2. Okay, so essentially what we're doing is we're going to find all the ways that it's changed from the original. So the first thing I like to do is write my parent function is the square root of x, and I like to draw the little graph of the square root of x. So it intersects at 0, 0 and goes up 1 over 1 and then slowly rises out like that. So that's my parent function. So I'm actually going to choose to take my blue colors and show the rest of my transformations in blue. Okay, or purple, you can choose. Alright, so my transformations here are a -3. So we follow PEMDAS, so we're doing the -3 is the first thing that happens. So the negative switches it over the x-axis, and then it actually vertically stretches it. So instead of going up 3 or up 1 over 1, it's going to go up 1 or up 3 over 1. So on this one, it's down 1, so down 3 over 1. So our new function is stretched like that. Okay, the next thing is this plus 1 because it's grouped inside. So, oh, I should have done that first, but it actually won't affect it. So remember, for PEMDAS, you should do parentheses, which is anything grouped, and then exponents, and then multiplication, division, and then addition. Okay, so the plus 1 is just going to move us left 1, because remember, x is always lie. So we're going to move our graph left 1. So our new graph should rise up to 3. Oop. Okay. And then we are also going to be moving our graph up 2. So we already did the plus 1. Now we're going to do the plus 2 on the outside, which just means to move it up 2. So that would be 1, 2, 3, 1. So this here is my final, and I'm actually going to put a different color on that so I know that this is the final graph. Another way to do this is you can do all of what you would know and do them individually on separate graphs. So you could do the -3 on one graph, and then the +1 on the next graph, and then the +2. So you would do like a series of graphs. Okay. All right. So example 3 is analyzing the graph, and it's a really good one. So you should pause the video and take some time to do this if you have time. And example 4 is the same thing we've been doing, but it's an inequality. So I am going to show the picture of that real quick, but I'm not going to do it. So an inequality just means that it's going to be shaded on the region that it's valid. So y has to be less than, so we shaded where y is less than underneath that. But the graphing is still the same as what we've done. Okay, the next thing we are learning is graphing the cube root function. So graphing the cube root function, cube root has a parent function that looks like this. And remember, the cube root is got the 3 as the index, and then just a regular x as the radicand. And we could write this as x to the 1/3. Remember, we can do fractional exponents for roots. And you can see that this actually has an extra piece. So we can actually have negative numbers under odd roots, and this is going to be the parent for all odd roots, just like the square root is the parent for all even roots. So any odd root is just going to look like some expanded version of this. And the domain for this is all real numbers, and the range is all real numbers. All right, let's do example 5. And just like with square root functions, you can transform these just like anything else. So we're going to move our note paper up, and we're writing example 5. And it's on page 326. Okay. So it says graph the function. And a is 1/3 the cube root of x. So we're going to put that over here, graph the function, which is 1/3 the cube root of x. Okay, sorry, so the thing I forgot would be something useful to put in your vocabulary again would be that parent function for cube root. So cube root of x. I'm going to put a little picture of the graph over here. And this is the parent function. All right. Okay, we are going to be doing example 5. All right, so we start with the parent function. Which just looks like the cube root of x. So cube root of x. And the only thing that's happening to that parent function, and again, I'm going to put my transformations in blue is this 1/3, and that is going to be a compression because it's less than 1. And so my slope, instead of being 1, 1, is going to be up 1 over 3. And so same down here, 1 over 3. So it makes this much closer to the axis, as you can see. So it's like squishing it, compressing it. All right, so that is A. So we can write B. So B is the cube root of x to the fifth, or x plus 5, sorry. The cube root of x plus 5. All right. So B, cube root of x plus 5. Okay, so my parent function again is just going to be that cube root, which looks like this. And the only thing that's happening, I'm going to put in blue, is my plus 5. And that is grouped inside with the x, so it's going to move in the left and right. So it is a positive, so it's going to move left. So we're going to move this 1, 2, 3, 4, 5. And we're going to graph the exact same thing over here. So this would be our new function. All right, so we are going to move on and we're going to go to 6-5, which is on page 333. There are still some good examples. If you have time, you can pause the video and work on those.
All right, so we're back and we are doing lesson 6-5 now. So we are on page 333 in your own book. And we are now talking about properties of radicals. And again, we've already talked about radicals quite a bit, how radicals can be rewritten as fractional exponents, and that to add and subtract radicals is what we're going to be working on today. So we are talking about how math with radicals is very similar to adding like terms. So if I had 2x squared plus 5x plus 6x squared, I could only add my x squareds together because they are the same type of term, and I would just add my two front numbers together. So 8x squared. And again, they're similar because you can actually rewrite your radicals as exponents. So we have a couple of different properties. We have the product property of radicals and the quotient property of radicals. The product property says that for any radical that is multiplied under the same radical, then you can separate them into two separate radicals with the same index. And then same thing for the quotient property. If they're divided under one radical, you can actually separate them and divide them as two separate things with the same index. Okay, so that being said, we are going to write that in our equations or vocabulary portion, and we are writing it in green. So make sure you have your color in green. So we're going to say product property before we get too far, I'm going to write that this is 6-5 up here, and that the date is 12/3/23. Okay, so product property is if we have things multiplied under a radical, we can separate them under the same index radical. Okay, and then our quotient property. So if we have things divided, we can separate them with two separate radicals with the same index. Okay, so those are things we're going to need to know throughout this, and so that being said, we are going to, I also just want to talk about adding and subtracting. So we're going to skip ahead to page 334. And it has right at the bottom, it says learn, adding and subtracting radical expressions. So radicals can be added and subtracted the same manner as monomials. So this is what I just showed you. So like an x squared can only be added to an x squared. And so if you have a cube root, it can only be added to other cube roots. And so it would have to be the same type of cube root. So if we come up here, it says, although two radicals such as square root 18 and square root 32 may not appear to be the same radical, if you simplify each radical, you can see that radical 18 is 3 radical 2. Again, this is done by our factor tree. So we take out a 9 and a 2, and this would be a 3 and a 3. So we pull out the 3, and the 2 stays in the radical. So remember, we've done that quite a bit before. So 3 radical 2 is what it simplifies to. And then the square root of 32 will actually simplify to 4 radical 2. And now they have the same radicand, that radical 2. So we could actually add those together to equal 7 radical 2. So as long as it has the same radical, it's like the same x, like x squared x. So 3 radical 2 plus 4 radical 2 is thinking of it like 3x plus 4x. The x just stays the same, and you just add the numbers afterwards. So 7 radical 2. Okay, just wanted to talk about that really quick. Okay, so let's do a couple of examples from this module. Okay, so example 1, it says simplify each expression. So remember, we always write in black. The example 1, and this is on page 333. Okay, and it says simplify, and A is the cube root of negative 27, A to the 6th, B to the 14th. Okay, and we're going to write that over here. A, cube root, and I'm going to space them out a little bit over here. Negative 27, A to the 6th, B to the 14th. Okay, I spaced them out just because my factor trees can get kind of messy. Okay, so basically, we need groups of 3 for a cube root, or we need cubes to pull them out of the cube root, because cubes will be canceled by cube root. So I'm going to factor tree and try and make my groups of 3. So I can pull out negative 3, and that would be a 9. And I could actually do a negative 3 times a negative 3. And if you'll see, there are 3 negative 3's here. And so a negative 3 can be pulled outside the radical. And there's nothing left over, so the numbers are gone. And then this a squared, we're going to have a cubed times a cubed and a cubed, right? So a cubed is what we're trying to pull out. And so we can pull out an a from this and an a from this. So a squared is what we pull out because there's 2 a cubed groups. So b to the 14th. 14 is not perfectly divisible by 3. So what I'm going to do is write this as b to the 12th, because I know that's divisible by 3, and b to the 2nd. So this would be a cubed, or sorry, a to the 6th, a to the 6th, and each of those would be a cubes. Okay, and these a cubes are the amount of a's that I can pull out. So a to the 4th, or sorry, this is b's. Haha, b to the 4th this whole time. B to the 4th is what I can pull out, and this b squared has to stay behind inside that radical. Okay, that is our answer. Okay, let's switch back to black and write example 1b. So b says the square root of 75 x to the 12th and y to the 7th. And make sure you rewrite it on this side. Radical 75 x to the 12th, y to the 7th. So we're doing the same thing here, but remember, don't forget to switch to red. We are, the only thing with B that we didn't do with A is remembering that this radicand is 2, or I mean this index is 2. So we're trying to have groups of 2. So I am going to pull a 5 out here, and I believe 75 divided by 5 is 15. And then we can take a 5 and a 3. So as you can see, we have a group of 2 5s, and that 5 can be pulled outside of the radical, whereas the 3 has nobody, so it has to stay. And I should have spaced these out. My x to the 12th, I can pull 6 groups out of 12. So oftentimes, a lot of the ways people do this is they just take this 2 and divide the 12. So we got x to the 6th. And this 7 is not perfectly divisible, so I'm going to write it with 2 different ones that are divisible. So this is going to be 3 groups of y squared, so y cubed, 3 groups, and then the y is left over. So our 2 things left in the radical are going to be 3 and y. Do example 2. So example 2 is good to see because, again, we can actually separate these. You could have done that with A. I just feel that it's just as easy to do it the way we did it. So example 2, page 334. It says simplify. And A is the cube root of 24 a to the 6th over 125. Okay, and we're going to rewrite that over here. A, the cube root of 24 a to the 6th over 125. Okay, and remember to switch to red. So using the quotient property that we wrote down up here, we can separate this into the cube root of 24 a to the 6th divided by the cube root of 125. Okay, and this just makes it more simple. We can do it the way that we have been doing it. So remember, with a cube root, we need to get groups of 3. So this is going to be 3 divided by 8, 4, and 2, and this can be 2 and 2. Here, I'll rewrite this a little lower. Cube root of 125. So 4 can become 2 and 2. So we have these 2's and this 2, so the 2 can come out. Okay, and then the 3 will stay inside the radical. Okay, and then a to the 6th, that's going to be 2 groups of 3. So a 2 groups. And then we have our cube root left over with a 3 left inside. Okay, now we're going to do the denominator. So I'm going to divide by 25, and that's going to be 3. No, not 3. 5, sorry. And this is going to be 5 and 5. So we have all of these 5. So this is actually just 5, because there's no radical left. So this would be our most simple answer here. If you could divide the 2 and the 5 evenly, you would, or if there was any a's to cancel, you would. But in this case, there aren't. Okay, I am going to let you do B, so if you guys have time, pause the video and do B by yourselves. Okay, now we're going to do example 3 and 4, and then we're going to talk a little bit about rationalization. Example 3, and this is page 335. So it says simplify 6 radical 45x plus radical 12 minus 3 radical 20x. Okay, and then we're going to rewrite this on the other side. So simplify. 6 radical 45x plus radical 12 minus 3 radical 20x. Okay, remember we can only add and subtract like terms, meaning that they have to have the same type of radical. So let's simplify each of these to make sure to see if we can find any radicals that are the same. So this is a square root, which means I need groups of 2 to pull them out. So 45 I can divide by 5 and get 9, and then I'd have 3 and 3. So the 3's I could take out. So they would multiply with my 6. So I'd have 6 times 3, and then the 5 has to stay inside with the x because it doesn't have a buddy. Okay, and then this radical 12, I can pull out a 4 and a 3, 2 and a 2, and these 2's can come out, so this is just going to be 2 radical 3. And then this 20, I can pull a 4 and a 5 out, and then these 2 2's actually can come out. So we're going to have negative 3 times 2 radical. The 5 has to stay and the x has to stay. So 5x. Okay, so let's take the next step. 18 radical 5x plus 2 square root 3 plus or minus 6 square root 5x. So if you notice, this 5x and this 5x are the same. So now we can add these like terms. So 18 minus 6 is going to be 12. So 12 5x, or square root 5x, sorry, plus 2 square root 3, because it doesn't have a like term. Awesome. Okay, I'm going to switch to new page because I need more room. So 6-5 continued. Okay, and we're going to do example 4. And that's page 335 still. And it says simplify. Four times the 5th root of negative 10 x squared y to the 6th times 3 the 5th root of 16 x to the 4th y to the 4th. So we're going to rewrite that on this side. So let's see, 4 times the 5th root of negative 10 x squared y to the 6th times 3 radical 16 x to the 4th y to the 4th. Okay, so when we're multiplying, everything that's on the outside will multiply, and then everything that's on the inside will multiply. So our 4 and 3 are on the outside, so 4 times 3 is 12, and then the inside. So my numbers are going to multiply together, so that's negative 160. And then my x squareds, or my x's, so when you multiply, exponents add, so 2 plus 4, x to the 6th power, and then y to the 6th is going to go with y to the 4th, so y to the 10th power. Okay, and now we can simplify, and remember this is a 5th root, almost forgot there. So if we want to pull anything out of it, you need groups of 5. So we only have one group of 5 for my x's, so I can pull out one x, and there should be one left over, because we should have x to the 5th, x, and this is the one we're pulling out. And then our y's, we should have two groups of 10, or two groups of 5, sorry, y to the 5th and y to the 5th. So we are pulling out two groups. Okay, and then our 160, we are going to see what we can pull out of it. I see a 10, so I'm going to go with that first. Negative 16. So negative 4 and positive 4. 5 and 2. 2 and negative 2. 2 and 2. So I have two groups of 2 that I can pull out, and the 5 and the negative 2 are left over. So 2 times 2 out here. So 12 times 2 times 2 times x times y squared. And then I need to write everything that got left in the radical. So my 5 and my negative 2, so negative 10. And I also have one x left over, and then there's no y's. So to simplify this, we would have 48x y squared radical negative 10x. All right. Okay. So last thing in this section is we are going to be talking about, so example 5 is another really good one. If you have time, please do it. It uses the distributive property, which is the same as multiplication. Distribution is still multiplication, so I'm not going to do that one. But when you distribute, you have to multiply each piece by each piece. We are going to talk about rationalizing the denominator. So you guys have already seen this. In a denominator, you cannot have fractional exponents or negative exponents, and so you have to rationalize. And what that means is we need to remove the radical from the denominator. And you can do this by completing the fraction, which just means simplifying the radical. And they have some good examples of that up here. So, if I have the denominator being the square root of b, square root of 7, then I'm just going to multiply by that same square root of 7. If I have the denominator with some other root raised to the x power, I am going to complete how much that needs. So if this is the 5th root of 2, I would need to add, so we're trying to get that 2 to 2 to the 5th so that my 5th root can cancel. So I would take my 2 and I'd have 2 to the 4th, because 2 to the 1st times 2 to the 4th would be 2 to the 5th. So we're trying to complete that radical so we can cancel. So, and then it also gives you some information about conjugates, which we've already used. The conjugate is the opposite, meaning it has the opposite sign in the middle of the two. And those will cancel our radicals. Okay. The other way I like to think of this is 2 raised to the 1/5. So in order to complete this, I need 4 more fifths, which is why I use the 4 here. That's why this is a 4. So it just is completing the fraction to make a whole fraction so that it's a 1 instead. So I like to do that. It's easier in my brain than it is to do my what completes the radical, though they're the same thing. Okay, let's do example 6, where we rationalize a denominator. Okay, we're going to write example 6. Page 337. And it says to simplify the cube root of 250 a to the 6 over 7a. Cube root of 250 a to the 6th power over 7a. So there's several ways to do this. One might be to actually cancel your a value there, so that this is just a to the 5th power. Oh, and I need to switch to red. Sorry. And then we have this left over, and then we can separate it to the cube root of 250 a to the 4th power, and then the cube root of 7, which is completely simplified. We can't pull anything out of that because 7 is a prime number. So all we need to worry about is simplifying this, and we need groups of 3. So I'm going to do 25 and 10 because that looked the easiest, and then 5 and 5, and 5 and 2. So I have 3 5s that I can pull out, and then the 2 has to stay. So I'm going to write that over here. My 5 pulls out, and my 2 has to stay inside. Okay, and then I can put this as a cubed and a to the 1st, and my a cubed I can pull out, so I can pull out 1a, one group of a's. So 5a cube root of 2, and then I also have my a that stayed inside, over the radical 7, square root 7. So, again, I like to do this where I rewrite my radical 7, and I'm going to use blue here to show that I'm rewriting something, as 7 raised to the 1/2. That way I know what I have to multiply is another 1/2 to add together to equal a whole. So 1/2 plus 1/2. And remember, 7 to the 1/2 is the same thing as 7 square root of 7. So it just helps me to know what I'm actually multiplying. So I'm going to rewrite my thing over here. 5a times, oh, and this is a cube root. So this is 1/3, which would make this 2/3, right? I need 2 over 3, which rewritten as a radical would be the cube root of 7 squared. Okay, so now I'm going to rewrite this. I have the cube root of 2a, all divided by the square root of 7. And now I'm going to be multiplying by the, cube root of 7. The cube root of 7 squared. And as you can see, this 7 squared and this 7 will multiply to have 7 cubed. And the cube root of 7 squared up here. Okay, so the top, what is inside the radical multiplies. So I have 5a times the cube root of 2a times 7 squared. So 7 squared is 49 times 2 is 98a. Okay, and then these will multiply together to equal 7 cubed. The cube root will cancel, which is the whole point, is getting rid of that. And so this is just going to be a 7 on that denominator. So, like I said, this goes to the cube root of 7 cubed. The cube will cancel the 7, or the cube root, and that'll be a 7. Okay, so we could go through this again to make sure we can't simplify any further. The cube root of 98, so 98 is divisible by 2, which would be 49, 7, and 7. So there isn't any groups of 3 that I can pull out, so this is my simplest answer. Okay, so example 7 is using conjugates to do the same thing for rationalization. If you have time to do that, that'd be great. If you don't, that's totally fine. So we are going to move on to 6-6, which is solving radical equations. And again, we've actually already done quite a bit of this. So we already know how to get rid of a square root. It's by using a square. So we are going to move on to that, and I'm going to get another piece of paper. All right, so solving radical equations is on page 343. And it says step 1 is to isolate the radical on one side. Step 2 is to eliminate the radical by raising each side of the equation to the power equal to the index. So we've done this before. And then solving the resulting polynomial equation. Okay, let's do example 1. And remember, we write in black. I'm going to write at the top that this is 6-6. And it's on page 343. And the date is 12/3/23. Okay, so what we're writing here is example 1. It says solve the square root equation. So it says solve. Square root of 3x minus 5 plus 2 equals 6. Okay, and we're going to rewrite that over here. Solve the square root of 3x minus 5 plus 2 equals 6. Okay, so the first thing is to get that radical by itself. I'm going to switch colors because we're going to do our work in red. So we're going to subtract 2. So we get the square root of 3x minus 5 is equal to 4. And then in order to get rid of a square root, we're going to square it. This cancels. So we get 16 equals 3x minus 5. Then I'm going to add that 5. So 3x equals 21. Divide by 3. X equals 7. So this is just basic algebra that you've been doing. So make sure that your result doesn't result in an imaginary number. So if we plug 7 back in, we get 21 minus 5. Square root of that is 4 plus 2 equals 6. So as long as we plug this in and we don't get a negative under that radical, we're fine. And again, it's only even radicals that have that problem. If it's like a cube root or a fifth root or a seventh root, it won't have that problem. Okay. So we're going to do example 3, which is identifying extraneous solutions. And it says to solve x plus 21 under the square root equals 3 minus the square root of x. Okay, so we are going to get rid of that radical. Oh, sorry, I need to rewrite this. So solve the square root of x plus 21 equals 3 minus square root of x. So I'm going to square here to get rid of this radical, and I need to square this. So I get x plus 21 equals this squared. So this is going to be a FOIL problem. So 3 minus radical x. Oh, and I'm not in red. My goodness. So I'm going to put all of that in red. Sorry, everyone. Okay, and we are multiplying this by itself. So then when we do 3 times 3, that's 9. 3 times negative radical x is negative 3 radical x. Negative x times 3 is negative 3 radical x. And then my negative radical x times negative radical x, the radicals will cancel, the negatives will cancel, so it'll just be x. Okay, and then I'm going to combine these like terms. So I have 9 minus 6 radical x plus x. Okay, and then I have x plus 21 on this side. So I'm going to subtract my x to get my x's together, and that cancels that x. So I get 9 minus 6 radical x. Now I'm going to isolate that radical again. So I'm going to subtract 9. So 21 minus 9 is 12, which equals negative 6 square root of x. I'm going to divide by that negative 6. So this is going to equal negative 2 equals the square root of x. Okay, and we're going to square this answer. So we get 4 equals x. Okay, so this is our answer. And we need to check to see if it's extraneous, meaning if we plugged it back in, is it going to cause an issue where there's a negative under a radical? So if we plugged the square root of 4 plus 21 equals 3 minus the square root of 4, what we would get. So 4 plus 21 is 25. Square root 25 is 5. And then square root of 4 is 2. 3 minus 2 is 1. And this is false. 5 does not equal 1. So this is an extraneous solution. So no real solutions. And really what that comes from is at this point a square is not going to equal a negative, and so it's going to come up with this extraneous solution. Okay, the rest of the lesson talks about graphing, and I would encourage you to take a look at it. We're not going to write any of it, but we are going to take a look here. It gives you instructions on how to graph, and again, we've graphed already. But whenever you write the cube root in a calculator, sometimes it's hard to find the cube root. So when I type this into the calculator, I would write 2 parentheses 3x minus 4 raised to the 1/3. And make sure you put that 1/3 in parentheses, plus 1. And it should give you this graph, and then you can use the calculate features to find the zeros and the table features to find any value that you need. So it gives you instructions, but like I said, one thing it doesn't tell you is that sometimes it can be very difficult to find how to use the cube root. And what I do is I just put in the fractional exponent. That would be the same thing. All right. I hope you guys are doing well. If you need anything, please email me. Good luck.